right, now we're going to look at geometric probability. A lot of this part of the unit is going to rely on prior knowledge of formulas for area of two-dimensional figures. So you may have to dust off some of the cobwebs for some of these figures. Please note that geometric probability is always going to be a percent. So we can put it into the form of the ratio comparing the part to the total, but we then have to go that extra step and convert it to a percent. Now, when we determine geometric probabilities and there's targetings involved, we're going to assume that the object lands in the targeted area unless you're told it doesn't, and that there's an equally likely chance that the object's going to land anywhere in the region. So there's going to come a time where it'll say what's the likelihood of it not, or what's the probability of it not landing in the shaded region. That is the only situation in which you do not assume that the object is in the shaded region. Every other time you assume equal chance, equally likely of landing in the shaded region. So for the example 1, your friend has an interesting collection of dartboards. If you throw a dart at random and it is guaranteed to hit the dartboard, but you only get a point if it hits the shaded region, what's the probability you will get a point in the dartboard below? And it's really to the right, not below. So first we have to determine the area of the entire dartboard. It's a square. We determine the area of the square by doing length times width. So we do 18 by 18. And using our calculators, we determine that that's going to be 324 inches squared. Now, when we look at the shaded region, the shaded part of that is a circle. If you do not know that area of a circle formula, it's 3.14 times radius squared. So we would have 3.14 times all the way across our circle is 18. That is your diameter. To get the radius, you have to take the diameter and divide it by 2. So in this case, our radius would be 9 because all the way across is 18, halfway would be 9. So to find the area of the circle, we're doing 3.14 times 9 squared, and we get that that is 254.34 inches squared. We don't want to round anything yet because if we round in the middle of the problem, it's going to alter the decimal point for our final answer. Now we are asked to determine the probability by comparing the area of the shaded region, 254.34, compared to the total region of 324. And we end up with 0.785. But if we remember, it's got to be converted to a percent, so we get that the percent would be 78.5%. Now, is this reasonable? Yes. The reason this is reasonable is because most of the dartboard is shaded. So if most of the dartboard is shaded, having a percent over 50% makes sense. Now let's take a look at a different example. If you notice, you have a rectangle, and inside of it you have 3 circles. However, the 3 circles are essentially holes that have been cut out of the middle of this rectangle. Now, we're only given one dimension of 18 inches, but that's 18 inches across the length of the entire rectangle. So if we know that all the way across is 18, that tells us that we could divide 18 by 3 for the 3 circles and get that each one is 6 inches across. Now, if the circles are 6 inches from left to right, the circles will also be 6 inches from top to bottom. And this is why, to do area of the rectangle, you would say 18 times 6 and get 108 inches squared. Now to get one circle, we know we're going to do 3.14 times radius squared. If all the way across is 6, to get r, we would say 6 divided by 2. And that's why we would do 3.14 times 3 squared to get 28.26 inches squared. But that's only for one circle. We have 3 of them. So we need to multiply 28.26 by 3 to get 84.78 inches squared for all 3 circles. Now, those 3 circles are like holes in the board, meaning they've been taken out of the entire board. So to get the shaded region, we take the entire board minus the 3 holes in the middle, and that's how we end up at 23.22 inches squared for the area of the shaded region. To find the geometric probability, we compare the area of the shaded region, 23.22, to the area of the entire region, which is 108, and that gives us 0.215, which is 21.5%. Now let's take a look at this figure. Hopefully you notice you have a shaded parallelogram on top and then a triangle that's been added to the bottom. The area of a parallelogram is base times height, so we're going to multiply to do area 10 times 32, and that's how we get 320 inches squared. For the triangle, we are told that from top to bottom, it's 17, but we know that this part is 10 inches because of what's written inside the height of this parallelogram. That means that the top part is 10 inches, the bottom part has to be 7 inches, indicating that the height of the triangle is 7 inches. So to get the area of the triangle, we do the base of the triangle, which is 32, times 7, divided by 2, or multiplied by a half, and that gives us 112 inches squared. To get the area of the total figure, we're going to combine these two areas, and we get 432 inches squared. Now the shaded region is just the parallelogram, so that's 320 inches squared. We didn't have to do any additional math to calculate that. For probability, we compare the shaded region, 320, compared to the total area of 432. When we put this into a decimal, we're going to have to estimate. We get 0.0741, so the approximate percentage is 7.41%. Let's take a look at the next two examples. So in this case, we have a triangle, and then there's a circle that's been cut out like a hole. To do area of the total figure, we have to do the area of the triangle, which if you notice across the bottom, they told you that to the left is 6 inches and to the right is 18 inches, meaning the total length of the bottom is 24 inches. So this means to do area of the triangle, we're going to multiply 10 times 24 divided by 2, or times a half, giving us 120 inches squared. Now to get the area of the circle, we know it's going to be 3.14 times radius squared. They told us that 6 was all the way across, so to get the radius, we have to say 6 divided by 2, which is 3. So that's why for the circle, we do 3.14 times 3 squared and we end up with 28.26 inches squared again. For the shaded region, we have to note that there's a circle that's been cut out. So we're going to take the entire triangle, take away that circle that's been cut out, and that's how we end up at 91.74 inches squared. That's our shaded area compared to the total area, giving us a probability of 0.7645, which is 76.45%. And for the next example, we have a triangle with a lot of measurements inside, and then a parallelogram that's been cut out the middle. So the first thing to note is that the height of the triangle is 2 plus 4 plus 6. And then for the base of the triangle, it's 16 plus 16. So 2 plus 4 plus 6 gives us a height of 12 centimeters. And 16 plus 16 gives us a base of 32 centimeters. So the area of the total triangle is going to be 12 times 32 divided by 2, or times a half, giving you 192 centimeters. And for the parallelogram, we have to do base times height. Well, note that the base is 8 plus 8. Which is 16, and the height's going to be 4. So we're going to do 16 times 4 to get 64 centimeters squared. Now for the total figure, that should read shaded area. And we are going to calculate this by taking our entire area of 192 centimeters and taking away that whole of 64 centimeters, leaving us with 128 centimeters. So the shaded area is 128 centimeters over the entire area of 192 centimeters, meaning that we are at approximately 0.6667, which is approximately 66.67%. Okay, moving on to example 6. During Raleigh's Freedom Balloon Fest, each balloon tries to land in a target zone. The target zone is a square that has a side length of 25 feet. The target zone is in the middle of a rectangular field that is 325 feet by 350 feet. We're asked to find the probability that the balloon is going to land in the target zone. So first we're going to draw a picture. So here is my rectangular field that measures 325 feet by 350 feet. And inside of it's a little square that has a side length of 25 feet. I'm sure your picture is much nicer than mine, but you get the idea. So we're asked to determine the area of the entire dartboard. In this case, the entire field. So to do that, we would multiply 350 times 325 to give us 113,750 feet squared. And we're asked to determine the area of the shaded region, or in this case, the area of the target. So we would find the area of the target by multiplying each side, and we would get 625 feet squared. So in order to determine the probability, we would need to compare, just as we did on the other ones, the shaded region, or in this case the target, compared to the total. And we end up with approximately 0.00549, which is approximately 0.549%. And we're asked, does this seem reasonable? Well, yes, it does. The reason behind this is that only a small part of the field has the target. So it only makes sense that the percentage should be under 1 or should be a small number. Now, moving on to the next one, you'll notice it says example 6, but in this case, we're going to change some dimensions. So all of the general pictures and information is going to be the same. However, this time, we are going to double the area of the target. So our rectangular field is still 325 feet by 350 feet, but this time, instead of the area being 1 square, we're going to have 2 squares. So we're going to double the area of the target. So determine the area of the entire dartboard, or in this case, field. It is still going to be 350 times 325, which is still 113,750 feet squared. And we're asked to determine the area of the shaded region, or in this case, the target. In this situation, the previous problem told us that the area was 625 feet squared. However, we were told that we're going to double it, meaning it is now 1,250 feet squared. And so we go ahead and calculate the probability by comparing the area of our new target to the area of the entire field. And once again, we're going to get a decimal, so that's not going to be very pretty, so we're going to have to use our estimation and rounding. And we find out that we're at approximately 1.09%. Now, we're not asked to calculate the new percentage of hitting the target if the area is doubled. What we are asked is, how does the probability change? Well, if we're comparing 0.549% to 1.09%, again, everything's going to be close and it's only going to be approximate because we've had to round. We should note that the area doubling means the probability doubles. So by doubling what our target was, we have now doubled our probability. We have increased it because we now have a greater chance of hitting the target. Now, in looking at page 22, you'll notice that it seems to be the same, except this time we are now asked what happens if each side of the target zone is doubled. So instead of just doubling the area, let's actually double the sides and see what happens. So we continue to draw our beautiful picture of our rectangular field that measures 325 feet by 350 feet. And this time, our square has now doubled by the length of each side. So each side is now 50 feet instead of 25 feet. So we're going to find the area of the entire dartboard, or in this case, the area of the entire field. And the field has not changed, so we still have that 350 times 325 will equal 113,750 feet squared. And we're asked to determine the area of the shaded region, or in this case, the area of the target. So that's going to be 50 times 50, which is going to give us 2,500 square feet. And we're asked to determine the probability by comparing the shaded region to the not shaded region. So we're comparing 2,500 to 113,750 feet squared. And once again, we know that it's not going to work out very pretty. So the decimal is approximately 0.02198, which is approximately 2.198%. We are not asked what is the probability. We are asked if we double each side, how's it going to change? So once again, everything's all approximate because we had to round. But if we're comparing about 0.5% to 2%, that means that the probability is now 4 times greater. So if you just double the area, the probability doubles. But by affecting each of the sides, we ended up really significantly increasing our odds and increasing the probability.